In Chapter 8, Part 4, Drawing Lewis Structures, we want to start to understand, instead of just a two-element bond, what happens when 3 or 4 or 10 elements come together to create a molecule. Eventually, we're going to start drawing in 3D. But first, let's think about how these elements come together in two-dimensional space using Lewis dot structures. So the guidelines. To draw the Lewis dot structure of a molecule. 1. Sum the valence electrons for all atoms. Take into account the overall molecular charge. This means if negative, add an electron. If positive, remove electrons. Basically, we know that the charge on a molecule comes from the number of electrons. So if your overall molecule has a -3 charge, you're going to subtract 3 from that. If it has or add 3 more electrons. If it is +3, you're going to subtract 3 electrons. So then you want to write the symbols for the atoms, connecting your adjacent atoms with a single bond. Then you're going to complete the octet around all atoms connected to the central atom. Remaining electrons go on the central atom. If there are not enough electrons left for octet on the central atom, multiple bonds are required. So it's a couple of other helpful hints. So we'll just write down here helpful. It would be helpful if I could spell that right. So let's try that again. Usually, the central atom is underlined or first, or, so we see it as a central atom is underlined or first. If it is 2 or 3 elements in a row, they are connected in order. If 2 to 3 elements, they are connected in order. So as we start to think about this will feel much more complicated in the beginning. The reason it will feel complicated is because we're building a skill set. By the time you take the next exam, you'll probably have drawn 100 of these. And that's going to help you get it right in that case. So the more examples you do, the better off you'll be. So let's do some practice. So we have 2 different examples. We have PCl3 and HCN. Now we've seen most of these molecules before, but in this case, we're going to start to think about it in this case. So the first thing we want to do, the number of valence electrons. So phosphorus has 5. And we're going to add 3 times 7, which is 21 for the chlorines, which gives you 26. Based on the underlined structure here, we know that phosphorus is in the center. We know that we're going to connect our 3 chlorines to that. And so now we need to just account for all of the electrons. So we're going to just start adding to make octet on any of our outer elements. So now all of our outer elements have octet, so we can see that there's, let me highlight this so you can see as I go, 2, 4, 6, 8 electrons around chlorine, 2, 4, 6, 8 here, 2, 4, 6, 8. Now, if you total that up, we've only used 24. And so we need to use the other 2, but based on the rules, that puts the last 2 here on phosphorus. And if we switch back to our highlighter, we can see that there are 2, 4, 6, 8 electrons around phosphorus. Now, you do not need to highlight all of those every time. I'm just trying to show. So what we can see is we've fulfilled the guidelines. Everyone has octet, everyone's been connected. So let's look at HCN. So our valence electrons are 1 plus 4 plus 5, which gives us 10. Carbon is our central atom, so we're going to plop it in the middle and connect to everybody else. So we're going to follow our directions. I believe we're on step 3. So we're going to complete the octet around all atoms. While hydrogen has octet, it has 2 electrons. and we've used, so now nitrogen has octet and we've used, let me count them up, 2, 4, 6, 8, 10. So we've used all of our elements, all of our electrons. So I'm going to come back through and erase all of this, the red lines, so that they're not confusing, so that we can come through and let's calculate octet. So nitrogen has 2, 4, 6, 8. We're good to go. Carbon has 2, 4. So carbon does not have octet, but nitrogen does. So we're going to need to create more than one bond between them. So we are going to use multiple bonds to create or achieve octet. So in order for carbon to have octet, it needs to have 8 electrons. So we're going to have to get carbon and nitrogen to share. So we're going to see some of these migrate into the center to where we see something that looks like this. And when we come in, we can calculate octet and we can see that nitrogen has 2, 4, 6, 8, and carbon has 2, 4, 6, 8. Now, I know that the ability to determine whether or not it has a triple bond is difficult. The more of these you draw, the more likely you are to notice that that's possible. Only certain elements can make double bonds. So more often than not, you will see leftover lone pairs or leftover electrons turn into bonds. By the end of this, it will make sense. So what happens if your element had a charge? So neither of the ones we started with had a charge. But we might have to calculate something called formal charge. So if we look at our BrO3-, it has a negative charge. One of those elements probably needs to have a negative charge, or maybe one or more. So to figure out which of these elements has a formal charge, meaning it is negative, which is different than a dipole moment, we need to calculate that. So to calculate the formal charge, the equation I like is formal charge equals the valence electrons minus half of the bonding electrons and all of the non-bonding electrons. These are otherwise known as lone pairs. Lone pair E-. So this equation is going to be different for every element in the compound. And so we're going to have to take it into account. So let's look at BrO3-. So the valence electrons here are going to be 7 plus 3 times 6 for oxygen plus 1. This is for our negative charge. So that gives us a total of 18, 19, 26. And so now we're going to put bromine in the center, connect it with our oxygens. We're going to go ahead and use up our extra electrons. And so at this point, we have used all of our electrons. Now, when we look at this, we're going to ask, does everyone achieve octet? And so if you look at any of our elements, 2, 4, 6, 8, 2, 4, 6, 8. Now, I'm not going to do it for all of the oxygens because in this case, they're all the same. But we know that there's a negative charge. And the question is, where is the negative charge? What is it? Which element is it on? Or is it on more than one element? So we can start to calculate that. So in this case, we want to calculate the formal charge for oxygen. Now, all of these oxygens are the same. And we're going to calculate it for bromine. So for oxygen, the number of valence electrons is 6. Then we're going to subtract half of the bonding electrons. So for any one of these, the bonding electrons I'm going to highlight in red. So there are just 2 electrons in a bond. So we're going to add half of 2. And we're going to add to that all of our lone pair electrons. So in this case, we'll highlight them in yellow. So there are 6 of those. And you can think about this as the number of valence electrons minus what electrons any element has. So because there are lone pair electrons, Oxygen owns those, but you only get half of the bonding electrons for formal charge. So if we do 6 minus 1 minus 6, that gives us a negative 1. So we have a negative 1 charge on an oxygen, or really all of the oxygens are the same. So for bromine, 7 valence electrons minus half of the 6 bonding electrons, 1 for each element, minus 2 lone pair electrons. So 7 minus 3 minus 2 gives us positive 2. So we would actually redraw this structure, and I'm only going to redraw it because I've doodled all over the other one. We want to make sure that all of our lone pairs are around. Don't forget, you cannot, if you would like full credit, use the lines that indicate lone pairs in my course. So we have all of these, and now each of our elements is going to get a charge on it. And so overall, we see that we have 3 negative charges and a 2 plus, which sum together give us a negative 1 charge. So if we were to consider CO2, we're going to go ahead and follow the rules. So the valence electrons in this case are 4 plus 2 times 6, which gives us 12 plus 4, which is 16. When we draw our structure, we're going to set this up. So now we've used all of our electrons, but we can see that carbon does not have octet. So we could use double bonds to give it octet or triple bonds. So we can create this molecule. Or oxygen, carbon, oxygen. So the question becomes, which of these is more correct? So which is correct? It's all going to come down to formal charge. So the thing is, we want there really not to be formal charges if the molecule doesn't have a charge. So let's look at our first structure, and I'm going to label OA and B in that first one. And I have done that because they are different. If they are the same, like we see them in the second structure, we don't actually need to calculate the formal charge for both independently. So the formal charge for OA is 6 minus half of 2 minus 6, which gives us negative 1. The formal charge for carbon is going to be 4 minus half of 8, which is 0. The formal charge of OB in this case will again be 6 minus half, in this case of 6, minus 2, which gives us a charge of plus 1. So we end up with a neutral molecule, but we see that we have a plus charge here and a negative charge here. That's not really balanced, but let's take a peek at our second one. So the formal charge of carbon, in this case, is going to be 4, again, minus half of 8, since there are 8 electrons around it, which gives us 0. The formal charge of oxygen is going to be 6 minus half of 4 minus 4, which is 0. So there are no charges here. But in the previous structure, there are charges. So the most preferred structure is going to be the one where the formal charge is closest to 0, or it matches what you have in the structure. But a Lewis structure where the negative charge resides on the most electronegative atom. So the first structure here violates multiple things. It has a formal charge on 2 elements, but the more electronegative atom, oxygen, has both a negative charge and a positive charge. So the most preferred structure is our second structure. So the most preferred structure is going to be the one where there are no charges, or that the charges reside on the most electronegative atom. So let's look at a couple other examples. So for NO2-, the number of valence electrons is 5 plus 2 times 6, plus 1, which gives us 18. We're going to put our nitrogen in the middle, connect our oxygens. So now we have 8 plus 8 is 16. We have 18 electrons. So if we look at nitrogen, it does not have enough electrons. And so we're going to donate from one of these to get this structure. So now each element has octet, but we can obviously tell that this is not exactly evenly balanced. It doesn't look the same, but let's look at our formal charges. So we're going to label our oxygens A and B again so that we can tell them apart. The formal charge of nitrogen is 5 minus half of 6 minus 2, which equals 0. We're on the right path. The formal charge of our OA is 6 minus half of 2 minus 6, which gives us negative 1. And the formal charge of OB is 6 minus half of 4 minus 4, which is 0. So we end up with a negative charge on a single element, not more than one, and only one of them has this charge. We will talk about in a later video whether or not there's a difference between OA and OB. What about for HClO2? So first we're going to total up our valence electrons of 1 plus 7 plus 2 times 6. So we have 12 plus 8 gives us 20. So in this case, the chlorine is going to be in the center. And we're going to connect everything to it. So we're going to use up all of our 20 electrons. So now we've used 8 plus 8 is 16 plus 2 more is 18. So in this case, we're going to end up with 2 electrons on the chlorine. So now our oxygens look the same. So we're going to look at our formal charge of oxygen, which is 6 minus half of 2 minus 6, negative 1. The formal charge of chlorine is 7 minus half of 6 minus 2, which gives us plus 2. So we end up with a negative charge on each oxygen and a 2 plus charge on the chlorine. And so this falls into the correct scale because each oxygen, which is more electronegative, contains a negative charge, and this molecule is fully neutral at the end. So the last one we have is SO3 2 minus. So our valence electrons are 6 plus 3 times 6 plus 2 for our electrons. So 6 times 4 is 24, 26. So we'll put our sulfur here in the middle and add 3 oxygens. And we're going to use a little eraser over here because that looks like we've got like 9 electrons happening. Make those a little bit bigger. So we've used 24 of our 26 electrons, and then we're going to add 2 more here. So now everyone has octet. So the formal charge of oxygen is 6 minus half of 2 minus 6, negative 1. The formal charge of sulfur is going to be 6 minus half of 6 minus 2, which equals plus 1. And so we can have a negative charge on each of these and a positive charge here. Now there are ways that you can change this, and we will talk about that in the video on resonance. But remember the guidelines and use them as you create any structure.